This is an action-packed video where we go completely hands-on and fine-tune Qwen 3.8 27 billion, the brand new 27 billion dense model from Qwen entirely on our own custom dataset and on a single GPU where I am running this Ubuntu and the GPU is with 48 GB of VRAM. This is Fahad Mirza and I welcome you to the channel. So what we are going to do here, no theory, no slides for long, we go straight to the terminal and build the whole thing end to end, which you can see on this screen. We create our own data set from scratch, which is this, and I will tell you how you can create it too if you are following along. Install everything live, train the model, watch the loss drop in real time, export it to gguf, and then run a before and after test so you can actually see what fine tuning changed. And the best part, you can follow along and do this on your own machine by the end. So let's not waste a second and jump right in. I already have shown you my configuration. So what I'm going to do, I'm just going to install Unsloth. And if you don't know what Unsloth is, we have covered it a lot on the channel. It is a library that makes fine tuning large models dramatically faster and far lighter on VRAM. So a 27 billion model fits on a single card, and the main alternatives are Hugging Face TRL with PEFT, Axolotl and Torch Tune. We already have covered all of them. If you don't want to use Unsloth, no worries at all. Same process, but a different tool. And if you don't know how to use that tool, we have covered it on the channel a lot. And by the way, while you are there, just go to the home page or first pinned comment and become the channel's member, as that helps keeping the lights on. And recently, I have also started this free weekly AI newsletter, which you can subscribe at fahadmirza.substack.com. And if you're looking to rent a GPU, check the link of Massed Compute in video's description. Meanwhile, our Unsloth is installed. Everything is installed. Now let's start our process. In the whole game of fine tuning, the first step is to create your dataset. Look at your screen. This is the dataset about me. Before we train anything, we need data, right? And this file right here is it. A dataset in fine tuning is simply a collection of examples that teach the model how you want it to respond. Each line in this file is one example, and if you look at the left, its data file extension is JSON-L. So JSON in each and every line. Let me scroll to the right to show you. So you see we have instruction, we have input, and then we have output. So what is happening here is that JSON object per line is showcasing one feature about myself. I'm using a simple structure, an instruction which is a question or prompt, and an output which is the answer I want the model to learn. So every line is basically a question and answer pair. The reason this format is so popular is that it's clean, easy to read, and training tools like a TRL, Unsloth, and various others, TorchTune, can load it directly without any fuss. And creating your own is genuinely this simple. You open a text file, and for each thing you want the model to know, you write one line with your question and the answer you would like to give. You don't need thousands to start. Even a few dozen good, consistent examples like these are enough to noticeably shift how the model talks about a topic. Now, I have built mine around who Fahad Mirza is using only public information. So, after training, the model will answer that question in my words. So, the thing is that you can increase it, but I want to keep the demo short. For a production workload, I would highly suggest go with 500 to 1000 and even more just to fine tune it properly, and you don't need to do it manually. That is why we have all of these LLMs. Just throw it to any local LLM and it should be able to create this JSON-L format too. You just throw raw data, tell it what you want it to do, and then massage it from there. The second part is the training itself. For training, I have created this simple script which is using Unsloth, our dataset, and I have divided it into sections. The reason is I want to explain it in as simple words as possible. And before even I do that, just bear with me. I'm just going to show you one thing very interesting which is extremely important in order to understand this whole rigmarole here. So we are talking about Qwen 3.8 27 billion. A big model like this has billions of internal numbers called weights. These are settings it learned during its original training or pre-training, and together they decide how it responds. Fully fine-tuning means adjusting all of these billions of weights, which needs multiple high-end GPUs and a lot of time and money, which of course I don't have because you guys are not becoming a member. Then we have LoRa. LoRa takes a smarter route. It freezes the entire original model so none of those billions of weights change. Instead, it inserts small new layers called adapters at key points inside the model. An adapter is just a tiny part of extra weight matrices, only a few million numbers instead of billions. During training, only these adapters learn. They sit alongside the frozen model and learn the adjustments needed to shift its behavior toward your data. So you get the effect of fine tuning while training less than 1% of the model. Then we have QLoRa. QLoRa adds one more saving. Before attaching the adapters, it compresses a frozen model from full precision down to just 4-bit, which roughly quarters the memory it takes up. The frozen model stays put in this compact form and the small adapters train on top of it. That compression is the final piece that lets a 27 billion model fit and train on a single GPU commodity one, which is exactly what we are doing here. So hopefully now the picture is clear. Now let me explain this script, and even before that, let me kick off this script and I will show you the output once we are done with that script reading. So while it runs, let's now quickly go through this script. And let me quickly give you the section by section. First, we are just importing all of these tools which we are going to use. And you can see that we have fast language model from Unsloth. We have dataset reads our JSON-L, SFT trainer and SFT config come from TRL library. SFT simply means supervised fine tuning, teaching the model from labeled question and answer examples. Torch is PyTorch, the engine underneath. Then we are loading the model in 4-bit. Remember that QLoRa where I told you that how exactly we freeze and compress the model. We are loading it in 4-bit, which is true. And then we have section 3 where we are attaching these LoRa adapters. This is the heart of LoRa. Instead of retraining the whole model, we are freezing it and bolting on tiny trainable layers. R equals 16 is the size. The rank of those layers, small means fast and light. LoRa alpha is a scaling factor that controls how strongly the adapters influence the model. Now target modules, all of these. This is where these adapters get attached. A transformer works by attention, which is a mechanism that lets the model decide which words to focus on. To do that, it builds three things for every token: a query, a key, and a value. QProj, KProj, and VProj are the layers that produce those. You can consider it as what a word is looking for, key as what each word offers, and value as the actual information carried. OProj combines the result back together, then GateProj, UpProj, and DownProj are the feed forward layers, the part that does the model's heavy thinking after attention. By adapting all of these, our small changes reach every important part of the model. Then we have LoRa dropout is equal to 0. We keep all connections active since our data set is small. Bias is none. We don't really train bias terms. Keep it lean. Use gradient checkpointing unsloth. It is a memory trick, and quickly a gradient is just the signal that tells the model how to adjust to reduce its errors during training. And then checkpointing saves memory by recompiling some of those signals. That's it. Then we have section 4, very simple. We are loading our JSON-L, then reshape each example into the exact chat format which Qwen expects. Every model expects a different chat format. And you see those IM start and IM end markers. These are special tokens that tell the model where the user's turn begins and where the assistant's answer begins. So we are wrapping every question and answer pair in that structure so the model learns the right pattern. And this is our whole trainer, and you can see this is primarily we are setting how the training is running, which we just kicked off. Batch size 2 with gradient accumulation 4 means we effectively train on 8 examples before each update, a way to get a bigger batch without memory. Warm up setup 5 eases the learning rate in gently at start. Num train epochs 3 means we pass over our whole data set 3 times, which is quite okay for a small set like ours. So it really learns. Learning rate is how big each adjustment step is. ADMW 8-bit is a memory efficient optimizer. The optimizer is what actually applies those updates, and the rest keeps the run stable and reproducible. This is where we are kicking off the training, which we already did, and then we are exporting it to gguf format, quantized to Q4KM, so we can run it locally or with Olama or whatever we want. So that is the whole thing from end to end. Training is in progress. Let me show you the VRAM consumption. So consuming is close to 19 gig of VRAM. Fine tuning is still running, and you can see that the loss is coming down. Loss is how wrong the model is on each batch. Lower means it's learning, as you can see here. And you can just watch it trend down as training goes. Grad norm is the size of the update step, stability check, and learning rate is how big each adjustment is, ramping up during warm up, then easing down. So let's wait for it to finish and then we will check out the model, the fine tuned one. Training is done. Now let's compare. So this is a comparison script which I'm going to use to load first the base Qwen 3.8 27 billion model and ask it who is Fahad Mirza. Now model has no clue who I am. Then it is going to load the same model with our LoRa adapter on top and ask the same exact question. So let's see the difference fine tuning makes side by side. Also check out this outputs underscore Qwen3.8 directory, which has our fine-tuned checkpoint 100. This is where our trained LoRa adapter weights are saved, and this is the result of our fine-tuning run. So let me take you here and let's run this compare script. So you see, this is the original one who has no clue about me. So let's wait for it to finish. And this is after fine tuning right in front of you live. This one knows about me, all about my YouTube channel. It is getting all that data from my data set which I gave it. So this is a correct response. If you look here, this generic model, the base model had no clue, and it actually admitted that it doesn't know who Fahad Mirza is. So look, a very small data set, a very small run, just a toy example, yet end to end and fairly realistic, which you would use in production. And you just saw how much a difference a fine tuning can make on your own data locally without any API calls. So that's it. Let me know what do you think. If this benefited you, you can also benefit the channel by becoming a member. Thank you for all the support.